This video is on free fall. I'm Mrs. Estock. Let's get started. What is free fall? Free fall is kind of a misnomer, meaning that an object in free fall doesn't necessarily have to be falling. What it means is that it's an object under the influence of gravity. And gravity pulls things downward. For that reason, we're going to start looking at motion not just in the horizontal direction, like we did in our sprint lab, where we looked at the acceleration of a sprinter running on a track. Now we're going to start looking at motion in the vertical direction as well, for objects that are undergoing an acceleration due to gravity. An object is in free fall when only the force of gravity is acting on it. Freely falling objects, by definition, have only gravity pulling on it. There are no other forces causing the object to change its motion. There is no air resistance, there is no applied force, there is no friction. The only force acting on an object in free fall is gravity. It doesn't say anything about the direction of movement, notice, in this definition. So that means an object in free fall could be moving up or down as long as only gravity is the force acting on it. As long as the object isn't moving too fast and is sufficiently dense with enough mass, it's okay to ignore air resistance in those situations. For example, on the picture that I have here, you have a swimmer or a diver jumping off of a high dive. In this example, the person isn't moving really, really fast, not like as fast as, let's say, an airplane. And they're massive enough where air resistance is not going to significantly slow down the object. If it was an object other than a human, for example, if you dropped a ping pong ball or a piece of paper from that skydive, then maybe air resistance would have more of a significant effect. But when we talk about free fall, we're talking about an object that is not experiencing a significant amount of air resistance. And in this special case of gravity, the acceleration is a constant, which we call g. We use a lowercase g to represent the acceleration due to gravity. And here on the surface of good old planet Earth, the acceleration due to gravity is 10 meters per second squared. That means that an object in free fall will gain or lose 10 meters per second of speed every second. So every second, the object's speed will change by 10 meters per second. We can solve for that speed using the following equation. V equals g times t, where v represents the speed or velocity of the object, g is a constant, 10 meters per second squared, and t represents the time the object has fallen. This equation is only valid if the initial velocity is 0. So this will work, for example, if the object is dropped from rest rather than thrown down with some initial velocity. Well, why is it that objects with different masses accelerate at this constant rate? The force of gravity causes objects in free fall to all accelerate at the same rate, regardless of their mass. This number, 10 meters per second squared, is truly a ratio of the object's weight divided by its mass. Because an object that is more massive, say an elephant, has more weight and more mass, if you take its weight divided by its mass, you get 10 meters per second squared. If you were to take a smaller object and calculate its acceleration the same way, because it has a smaller weight and a smaller mass, those numbers divide out to equal the same value, 10 meters per second squared. Even though Galileo performed this experiment years ago, hundreds of years ago, by throwing different massed objects off the top of the Leaning Tower of Pisa, and proved that all objects, regardless of their mass, fall at the same rate. For some reason, this is still a difficult concept for us to wrap our heads around, probably because we're thinking of how air resistance might influence objects with different masses. But if we look only at free fall, only objects that are being accelerated by gravity alone, without significant air resistance playing a role, they all accelerate at 10 meters per second squared, which is why we consider that a constant value. All objects, regardless of their mass, accelerate at this rate. Let's try a practice problem. If you drop a ball from rest from the top of a cliff, how fast will it be going after 3 seconds of falling? Take a moment to pause the video and use the equations presented previously to solve for how fast the object will be going after 3 seconds of falling. Pause the video, take out your calculators, and complete the problem. If you drop a ball from rest at the top of a cliff, after 3 seconds of motion, how fast will it be going? Let's think this through, thinking about how the acceleration due to gravity will accelerate the ball. If the object starts from rest and falls for 3 seconds, every second this ball will gain 10 meters per second of velocity. So if it starts from rest, the initial velocity will be 0 meters per second. After 1 second, it will be traveling 10 meters per second. After 2 seconds, it will be traveling 20 meters per second. And after 3 seconds, it will be traveling at 30 meters per second. So the final answer here is that it will be traveling at 30 meters per second at a time of 3 seconds. You can calculate this using the equation presented previously by taking the time, which is 3 seconds, multiplied by the acceleration of gravity, which is 10. So 3 times 10 also gets you that final speed of 30 meters per second. Let's say that you are presented with a question that asks you to calculate the time it takes for an object to free fall a certain distance. To do that, we can use the following equation. T equals the square root of 2d over g, where d represents the distance fallen, g is still our constant of 10 meters per second squared, and t is representing the time it takes for the object to fall. Like before, with our other equation, this one is only valid if the initial velocity is 0. So it must be an object that is dropped from rest in order to use this equation. Let's try a practice problem using that equation. A ball is dropped from rest from a 125 meter tall building. That's a very tall building. How much time does it take for the ball to hit the ground? Take a moment to use the previous equation to solve for the time it takes the ball to hit the ground. Take a moment to pause the video to complete the problem. For this problem, let's use the equation t equals the square root of 2d over g. When we plug in our values, notice that everything is underneath the square root sign. So under the square root, we have 2 times 125 meters divided by 10 meters per second squared. Mathematically, you want to do all of the math under the square root sign before you take the square root of the number. If we simplify this step by step, 2 times 125 is 250, divided by 10 is 25. We can then take the square root of 25 to get our final answer, a time of 5 seconds. So it will take this ball 5 seconds to fall 125 meters. Let's try another practice problem. A ride at an amusement park drops riders and they free fall 320 meters before the ride slows them down before reaching the ground. For how much time are they in a state of free fall? Take a moment to pause the video and solve the problem for how much time they are in a state of free fall. Again, we are going to use the equation t equals the square root of 2d over g. When we plug in our values, we have 2 times the distance fallen, 320 meters, divided by 10 meters per second squared. Mathematically, we simplify everything under the square root sign first. So our next step is taking 2 times 320 meters to get 640. Next, we will divide 640 by our acceleration due to gravity, 10. After doing that, we get 64, and the square root of 64 gives us our final answer of 8 seconds. That is the end of today's video. Thank you for watching. If you have any questions, I can answer them when I return to school on Monday.